So basically, we live in very interesting times. So we have access to AI models which are able to perform complex tasks. For instance, I recently asked an LLM how to cut bread and got a very detailed answer, and what kind of knife to choose and how to hold it and what to do even if the bread is still warm and so on. And what if there is a special type of bread like a baguette, what kind of things to take into account. So a very interesting and very well informed answer for my question. So I thought, okay, very, very good. And on the other hand, I also reviewed some of the papers in the medical field, and some people studied the performance of LLMs in the medical context. For instance, they have asked, like their favorite chatbot, have there been any reports of implantation of a subcutaneous defibrillator immediately after cardiac surgery, and please provide references. Okay, maybe for computer scientists like me, this question is difficult to answer, but apparently the LLM answered very confidently, saying, yes, there have been reports of implantation of subcutaneous defibrillators immediately after cardiac surgery, and here are some references. Looks kind of good, but the problem is that these papers are not there, so they're kind of made up. They are hallucinations of the LLM. And there are a couple of more studies in this direction, saying that, or showing that sometimes these recommendations the LLM gives to the medical people are valid, but sometimes it mixes this kind of valid recommendations with things which it has made up or which are come from another context. So using these kind of models out of the box in high-stakes decision-making can be problematic. So it kind of reminds me of this kind of quote: "So not to be or not to be, to trust or not to trust." This is kind of the question. Or what can we, to put it in a different way, what can we do to increase trust in our models? And I think one component of it is to get a better understanding, to better understand what these models have learned, to better understand why they fail, and to do something about it, to also create methods which kind of allow us in a systematic way, in a systematic manner, improve these models, debug them, and potentially remove some information from them in order to get better, more trustworthy models. So this is some direction which I would like to talk about today. And I'm very much engineering oriented when it comes to XAI, so I think it's perfectly valid to have like different methods, different types of methods to highlight and explain different aspects of the model and its behavior. So sometimes people have the very idea that there is like one explanation, the true explanation, but I think it's not useful. It's much more useful to have a broad view of unexplainability and look at the model and its behavior from different angles. And this is what we want to do. So I had been very lucky to be kind of already in this first wave of explainable AI research. Of course, the field or the questions regarding explainability are even older. In the 90s, 80s, people also wanted to get some insights into the models. But kind of the first wave, which I call, which kind of came around with the revolution in deep learning, where people started using these models for image classification, and these models became very complex and bigger, more parameters. And this was kind of the time where people especially focused on this kind of method development. So we, in Berlin, like 10 years, I think we started with this work 2011 or so, also had the idea, we had some collaboration in some medical field, and the medical doctor, the histopathologist, wanted to understand what our methods are doing, whether they detect cancer based on the same features as he looks at, or whether these models have learned different strategies. So this was kind of the initial point. We started even at the time where people used support vector machines, Fisher vector methods, feature-based machine learning models. And then, yeah, this field kind of developed very quickly, and people use explanations for different purposes. So they use explainability to debug models. So this is a horse from a paper which we published in Nature Communications, where we showed that some of these AI models, which in this case won an international competition in image classification, was using like the wrong features. So they were classifying the horse image correctly as horse image, but not because of the horse, but because of a copyright tag in the lower right corner. And people at that, before they had access to these explanations, they were not really, didn't know about this. They said, okay, the classification results are correct, so my classifier works. But we also detected a lot of, many of these type of problems that, and also other people reported this, that these models pick up some artifacts which are kind of spuriously correlated with the class label, and often base their decision on that. And if you don't understand what your model is doing, it's very hard to detect these biases. You could say, okay, maybe why there is a copyright tag, maybe the people who created this data set didn't do a good job, but if you have like 100,000 of images, it's very hard to systematically avoid these kind of biases. And by looking just at one horse, at one image, with one prediction, we immediately saw that something is wrong here, that it's a correct prediction, but for the wrong reason. Recently, also, there was a very interesting Nature paper where people showed that they got new insights with explainable AI. So they developed a new class of antibiotics. So in drug development, these kind of methods can be used to get a better understanding, to create new hypotheses about the functional groups, for instance, in chemical molecules. And the better you understand your data, the better you understand the functional groups. Maybe you can come up with new drugs or new improved understandings. And this is something people talked about for a long time, and always right in the intro, explainable AI is good for debugging, for getting new insights. But these guys, I think, were the first really showing that they can get new scientific insights. Often people just validate what they already know, but learning something new from the model is, I think, a dream of many scientists. And these methods can potentially be used to visualize, to highlight what they have learned. And this, if it's something useful, if it's not like a clever Hans artifact, then you can potentially get a better understanding of your data and the physics or the chemistry or the biology behind it. Also from legislation perspective, there is a lot of people talking about the right to explanation and legal issues, and in certain applications, maybe the AI being used has to be explainable, has to provide some feedback, or at least, maybe it has to be benchmarked also from an ethical perspective, whether it's fair or not. So there is all these word of legal, social, ethical dimension, especially if we use AI models in interaction with humans, right? If they are used in selecting candidates for a job, or in making decisions which affect human life, this may be a strong requirement to really make sure that the process is transparent, or at least to some degree transparent. often the problem is that from a legal perspective, it's maybe easy to define it. So, okay, my model should be transparent, but what it technically means is often still a big mystery, and people are in the process now to figuring it out. But I think we need applications, we need to do it, and then we can get better understanding what we really mean by that. And what we recently became interested in is also to think about new ways to explain. Because here, I mean, what you see with the horse example, this is kind of a typical heat map or attribution map showing you what elements in the input are relevant for the output. So where the model is kind of looking at to arrive at its decision. While there are other types of explanations. For instance, you could try to explain the model internals. What has the model learned? What do individual neurons represent? But you could also, we call it like citation-based explanations, which I think can be very interesting for LLMs. So for instance, if you ask your model, what is the capital of Germany? Maybe it says, okay, the capital of Germany is Berlin. And you may want to know why. And the answer, I mean, if you just highlight the important words, if you say, okay, capital in Germany as important words for the answer Berlin, it's like an explanation in the kind of technical sense, but it's not providing you probably more trust in the answer, while referring to an external data set. Maybe the model has access to Wikipedia or to some other fact database and tells you, okay, the answer is Berlin because it's kind of written in this database, or it's written in the Wikipedia article. So this is something scientists and journalists also do, right? They provide sources for the claims. They make a claim and then they say, okay, this is my claim because there is kind of the source for it. And we are thinking about these new types of explainability, which we think can be very useful, especially for large language models. Okay, so today a lot of stuff which I will present will be based on LRP. LRP is the abbreviation for Layer-wise Relevance Propagation. It's a method, the paper which we published in 2015, which we kind of started working on years before. And basically the idea of LRP is to explain or to redistribute the output through the model until the input in a meaningful way. So basically what you have like an image of a dog. The image gets kind of classified as a dog. And what we want to do is we want to redistribute then the output dog backwards, layer by layer, to the input. And then the input kind of tells us which parts of the input were important for the classification. So how do we do this? We kind of measure the contributions, right? So we want to measure how much this guy, neuron J, has contributed to the activation of neuron K. And if we have these measurements, if we know how much the neuron in the layer before has contributed to the activation of the layer afterwards, we could use these contributions to just proportionally redistribute relevance. We say, okay, if this guy has contributed more to the activation of the dog neuron, it should get a larger share of the relevance, a larger percentage of the relevance. And this is what this kind of LRP rule does. So you kind of decompose, you kind of create this kind of messages, these flows, and then redistribute relevance layer by layer through the network. And you do it iteratively. Then you ask, okay, how much did this guy contribute to the activation of this guy and the activation of this guy? And then it gets some of the relevance from the next higher layer. And there is also a more theoretical interpretation of this process. I will not go into detail here, but kind of this kind of messages or this flow which we highlighted here can also be interpreted as a particular type of Taylor decomposition of the relevance neuron between layers. So there is some mathematical framework where kind of these ideas have been later embedded. So we first developed the algorithm, and then later we realized that it can also be described as a particular type of Taylor decomposition. Okay, and then the question is, of course, how to measure these contributions, how to measure the contribution of J to the activation of K. And there, over the years, we came up with different redistribution rules. We call them redistribution rules. And first, what we did is LRP zeros is say, okay, we take the activation and the weight. So the more this guy is activated, then that means it encodes something which is in the image, right? It may encode a feature, for instance, the eye of the dog, or maybe some other feature. And if it's activated, then it's kind of potentially relevant because it encodes something which is in the image. But maybe some other neurons are encoding like the wheels of a car, which are not in the image, therefore are not activated. So this activation is kind of one element. And then the second element is the connection between these two. So if, for instance, this guy is encoding the feature I, and feature I contributes to the prediction dog, or is important for the prediction dog, then the combination of these two is large, and therefore this neuron J should get a larger share of relevance. So we kind of came up with these rules, then we realized that this LRP0 can be mathematically unstable because you divide by a sum, which can be 0. So we extended things, and then we also created specific rules for specific layers. For instance, certain layers have specific properties. So for instance, after the ReLU, you have only like positive values or 0. Or if you're in image space, your values are bounded between 0 and 255 usually. So you have specific constraints in each layer, or convolutions have a specific structure. So you have specific constraints which we kind of try to build into this redistribution formula. And the cool thing is that you can map these kind of redistribution rules to this Taylor decomposition framework. But I will skip that. But basically what you have to keep in mind, we have these redistribution rules, and they can be used to redistribute relevance from output to input. And the cool thing is also that you are, as you see here, we are not only getting the heat map, but you also, if you perform this process, you also figure out how much individual elements of the neuron have contributed to the prediction. So you have all the relevance values for all the neurons in between, and for all the all the channels. So you know that for this, maybe for the prediction dog, this guy was very important, and this guy, and maybe this guy was not important. So you have all these values. This will become important later on. Okay, but we also thought, okay, for LSTM layers, they have a different structure. So you have like this input gates and forget gates and how to do the redistribution there. And we have a paper with Sepp Hochreiter where we kind of analyze different ways to do so, and it turns out that a certain way to do the redistribution makes kind of sense, and it can also be integrated into this Taylor decomposition framework. And then recently transformer-based models came up. They have even a different structure. They have like attention heads, right? So you have like a product, you have like a product here, you have layer norm and this type of operations. And then we thought, okay, how can we adapt LRP to these layers? So as you see, this is kind of the price to pay for this type of method. It's very efficient and it gives good results, but if you have a new architecture, you have to think carefully how to adapt it to these new types of layers. This is something which we kind of studied recently, and I will not go into detail here, but we have this year at ICML presented like an attention LRP paper, attention variant, which kind of takes into account the redistribution over this attention layers. And also here, I mean, you can also prove that this type of redistribution is consistent with this Taylor decomposition. And the cool thing is that if you want to explain this kind of transformer models, these big ones, or vision transformer, a lot of classical methods, such as smooth grads or gradient times attribution rollout or Ant-Man, which is kind of a perturbation-based approach, do not work so well. So this has several reasons. Either computationally, it's very costly to do the perturbations. If you think about having like multiple forward passes in the transformer, it can be costly. But also you have like different statistics, different structures. So taking the gradient is also not very, very reliable there. But in terms of faithfulness, this kind of attention LRP variant performs well. It also performs well in terms of computational efficiently. And it also allows us to explain the latent elements of the model. So as I said before, we not only are able to explain in terms of input attributions, but also tell which neuron has contributed to the prediction. So this is nice, and we have some results. I will not go into detail here, but I mean, you see for vision transformer, for Llama, for Mistral, for different types of models, the higher values are better. Attention LRP kind of outperforms the baselines which have been available, even like methods such as SHAP, which are quite popular, but or GradCam, or a lot of these classical methods like integrated gradients, they don't really work well for these transformer models. Also, qualitatively you see that this gradient times input types of gradient-based methods, smooth gradient, you get a lot of noise, and it's very hard to really derive some understanding from that. Okay, so this is kind of where we are. Also for text, I mean, we had here in text an explanation could look like this. So you have like a question, for instance, like a query. In what country is Normandy located? And what we added to the network, we gave the model a context, right? This is a context, a question, and the model correctly answered the question, France, and then we kind of explained the answer. So we kind of backtracked with LRP this answer token, France, and wanted to find out which kind of information in the context is relevant for this prediction. And you see that if you take integrated gradients, you get kind of a mess. Even for the simple questions, also input times gradients, but attention LRP performs quite okay. Of course, I mean, how to evaluate things and how to measure the quality of an explanation is something which I didn't mention here. I mean, we have like this faithfulness measurements here, but this is also a topic of active research. So in my opinion, an explanation is good if it gives you some kind of advantage, or if you explanation should be goal oriented. If you want to debug your model and if your explanation helps you in that, then it's good. But of course, it's difficult to measure this. But anyways, I mean, comparison to other variants, so also before even already 2017 and 21, people tried to apply LRP for transformer models, but what they didn't, I mean, what our method is doing is it lies within this deep Taylor decomposition framework, and a lot of problems which previous methods have in terms of stability, we kind of overcome. But this is maybe for detailed information, which we don't go into it. But I just want to make this point that having this mapping between the redistribution rule which you use and this kind of Taylor decomposition approach is something which we think is relevant and which is, at least in this case, gives us better results. Okay, so we are in principle able to explain transformer-based models. We are able to explain large language models, as you saw. with this method. And we can do it in a very efficient way. We can do it in real time. So we do not need to wait. For that, I even have a demo. We even have a demo which kind of, well, when you come to visit us in Berlin at some point, you can see it, and you will see that you can ask a question, you get an answer, and we also get some kind of citation-based explanation and tell you which part of the information is really relevant for the answer. Okay, but now we want to go one step further. We want to not only understand the decision in terms of attribution map, but also understand the encoding of the model and how these encodings matter for the prediction. This is something which we realized after some time when looking at these heat maps. For instance, you have like a bird classifier, and apparently like the reason why the classifier classifies this bird as a particular species is because of that, and it classifies this bird as a particular species is because of that heat map. But it's not really informative, right? If you would ask a human bird expert, you would say, oh, maybe this is this particular bird because it has a yellow belly and a very short beak, and maybe some types of feathers. So we humans describe things in concepts in terms of color, size, shape, and so on. And these heat maps only tell us where something is relevant, but it doesn't tell us what it is. Is it because it's black color, or is it because of the size of this? So we don't know. And what we recently published is a paper. We wanted to call it from where to what, from attribution maps to human understandable explanations through concept relevance propagation. So we kind of extended, or we built up on the LRP framework, and instead of looking at the heat map in input space, what we did is we kind of explained the model's internal representation. Because at least for images, it is well known that the higher layer of the network typically encode semantically interpretable features like objects or objects parts. And so for instance, what we wanted to do is we wanted to know, okay, what concept is encoded by this neuron and how much does this kind of channel contribute to the prediction. So the question of contribution we already have if we do the LRP pass, because LRP tells us that how relevant is this guy, how relevant is this guy, how relevant is this guy. We already get this when we do one LRP pass, but we don't know what concepts are encoded by this individual elements of the model. So how can we find out? How can we find out what concepts are represented in particular neurons of the model? There is work known under the name activation maximization. People now also call it mechanistic interpretability, or they rely on these techniques where the goal is to find out what individual elements, what individual neurons are, or what individual circuits in the network are encoding. And what people did is they found, for instance, some samples from the training data, from some external data set, which maximize the activation of this channel or of this neuron. And they say, okay, if these samples maximize the activation of this particular neuron, then they encode something which is encoded by this neuron. They encode some concept which is relevant. So we had this idea, we kind of extended this concept a bit. So instead of using the activation values, we proposed to use the relevance values. So we call it relevance maximization. But in the end, what we get is a set of samples or parts of samples showing us the role of this neuron in the prediction process. So for instance, here you see a collection of samples encoding some Chinese characters, and apparently they play a role in the prediction, and apparently they are encoded by this particular channel. So this is what we want to find out. So for instance, if we have like a bird, it's classified as a particular bird. And what we can do is we can identify the most relevant channels or neurons in some intermediate layer, for instance, the last convolution layer. And LRP tells us how much these channels contribute to the prediction. These are the relevance values which we saw before, which we redistribute. So we know that maybe this concept is the most important one, this one is the second most important one, and this one is the third most important one. And what we can then do is to use relevance activation, relevance maximization, to find, we call it reference samples, so to find images which kind of encode the concept which is represented by this neuron. And we even can pinpoint within this sample what is the part of the sample which is encoded by this channel. So for instance, here we see that channel 210 is kind of encoding some leopard type of texture. And apparently the fact that this bird has kind of a leopard type of texture plays a role, a significant role for the prediction. Also, this channel 10 is encoding red color because in all the samples which we got through our method, you see that the red part, the red stripe, is the relevant part. So we can derive from that this channel is encoding red color. So the fact that this bird has a red stripe here is relevant for the decision making. So we can do it like in this way, so we can break the decision into, at least for images, into human understandable concepts and can say, okay, this decision was made because of the red stripe, because of the leopard type of texture, and so on. And we can do it even for the whole prediction, for the whole network path across different layers. So we can say, okay, this bird was predicted as a bee eater because it is sitting on a branch, and the concept sitting on the branch is created from lower level concepts like horizontal bars or colorful feathers and so on. So you can even see how concepts create other concepts, how low level concepts are creating more complex concepts with these kind of approaches. And here is like an application. I think we can have. Or do you have like an urgent? This is a percentage of the relevance, right? So these percentages are quite low because you have like many neurons, and some of them may be redundant. So you could also apply something like a PCA on that, or some kind of decomposition method to combine neurons which are encoding the same concepts, and then the percentage would be larger. Here it's like individual elements. Okay, so one application which we saw is this. So we have like a prediction safe, it is correct predicted, and we see that some of the features like the handle here is important, but also there seems to be some Chinese characters in the middle here. And we thought, okay, what neurons are or what channels are encoding these Chinese characters? And we thought we found 6 of them, and then we did some reverse search. We thought, okay, for the other images in the data set, where do these 6 channels are also relevant? And we saw that there are other samples in the data set where these 6 channels are also relevant and where the Chinese characters are also there. So you can also search by the presence of this concept. You can say, okay, I've identified my artifact concept and I want to know in which other samples these artifact concepts are there. So we are now working on some extension of this idea, which I hope will be ready in a couple of weeks. But what we didn't expect is that in some other examples, like a puma or spider web, these 6 channels are also relevant, but there is no Chinese character. But from the kind of statistics point of view, the thin hair of a puma or the thin line of a spider web looks like a Chinese character, because the Chinese character is also like a very thin white stroke on background. So, I mean, at this layer at least, to the network is kind of invariant, whether it's like the hair of the puma or the Chinese character. So just to put it in different way, so if you just remove these neurons, we could maybe hurt classification performance for classes where these neurons should be there, should remain. So this is something which we didn't know before. Okay, so the next level of abstraction, so from individual explanations to understanding global behavior. So until now, I told you everything about single predictions. But what you can do is, of course, you can compute these concepts, these concept relevances. So we call it concept relevance vector. So you have all types of space shuttle images, and you kind of compute these concept relevances. So these are just the LRP values for some higher, some intermediate layer. And if you can map the concepts, the neurons to concepts, so for instance, you can say, okay, for this image, 20% was this pen-like form was important, but also the concept fire was important, and also the concept dust. Right, so you can compute it for the whole data set, and you can cluster. You can find then clusters of concepts combinations which lead to the prediction. And apparently the model learns to classify space shuttle based on concepts such as fire and dust, but only for certain classes, certain types of images, right? Because in these images there is fire and there is dust. For those images of a space shuttle, these concepts are not present, but there are maybe other concepts present, like a wheel, right? So by clustering globally in this concept space, you can determine these kind of structures, this kind of co-occurrences, and even this kind of sub-label structure. So even all of these images have the same label, space shuttle, they are composed of different concepts. And what we also didn't expect, for instance, we also applied it to ImageNet and VGG for the class lacewing. Lacewing is this kind of animal here. And apparently there is nice kind of cluster, but there is an outlier. So this kind of prototype 1 is an outlier in this lacewing class, because outlier in the sense that it is composed of other concepts. It is not composed on the same concepts in these images, these prototypes. And if you look closely, and if you know about like biology, and so you see that this is like a leopard lacewing butterfly. It is not a lacewing, but a particular type of butterfly, which means that people creating this data set mislabeled these samples. And we think that because they took these samples from Flickr and had like some automatic tags and relied maybe on the tags, on the labels there, this was kind of classified as a lacewing because it has lacewing in the name, but it is not the animal lacewing, but a leopard lacewing butterfly. The same you can see with the tiger. So this is kind of a tiger cat, but this is not a tiger cat, but a tiger, right? But maybe in the creation of the data set, these labels were mismatched, and this kind of animals were also labeled as a tiger cat, and therefore but in the concept space you see that they are different from the other ones. So they do not share the same concepts. And basically what we do now, or what we're interested in, is to really look at these concept spaces and to see what is the composition of our class and where are outliers, because these outliers can be indication of misbehavior of the model. Or you have like the class Pickelhaube, which is this kind of helmet from the First World War. And you can even create this matrix where you have prototypes in the columns and concepts in the rows. So you can say that maybe some of the prototypes encode black and white or show black and white groups or a uniform code, but there is no kind of Pickelhaube there, but it's just like the soldier code, and therefore these features are used, or even like this dome-like shapes are kind of used in encoding of this concepts Pickelhaube. So we had like this validation perspective on AI here. So we embedded this training predictions for the cartoon class, and we saw that maybe this is kind of this concept space. We clustered them, and we saw that some of the examples are outliers, and if you look at it, these kind of samples, so every point is a sample, and you see that these samples have a lot of cats in them. So they use kind of concepts which are usually not related to the cartoon class, or which, in addition, which are there, which are not there here. So you can very easily identify outliers in this way, and even within the proper cartoon class, you can see that maybe there is concepts related to some Chinese letters or some barcodes or so. So you can really decompose your prediction strategy and visualize what concepts are used, and as a human you can validate if it's useful or not. So what we really try to do is to save manual labor for the human expert, to not look at all the explanations individually. So in the past we had a lot of PhD students just looking at the explanations and trying to figure out if there is something. Now we have like these concepts, and we even have prototypes or clusters of concepts where the student can very easily, and it's kind of scalable. So one student can do the whole data set, whereas before we needed a lot of students. Okay, so but we don't want to stop here. We want to move one step further. So we have now the tools which I showed you to identify problems with the prediction, and we want to improve the prediction. So what we proposed recently is a reveal and revise framework where we model the artifact and also use methods to unlearn, to force the model to unlearn the prediction strategy. So just very quickly, so we have like these images of melanoma, skin cancer, but sometimes as medical doctors put some stuff on the skin, and this is picked up by the model, so we identified it by our tools, and then also forced the model to unlearn it. And then we did the next iteration, and there is a band-aid. Sometimes in the images, it is picked up by the model. We force the model to unlearn. Next iteration, and sometimes they put some ruler on the skin, and it's also picked up by the model, so we unlearned and had a more trustworthy model. So we try to involve the human, but to minimize the labor for the human. Okay, let's go now back to LLMs. So we applied the same ideas also to LLMs, or at least in a smaller scale, but we can also in LLMs get this concept level understanding. For instance, we can identify sentences which encode concepts represented by a neuron. So here you have like the neuron 256 in layer 18 or so, and these are the 5 sentences which mostly activated, and you can pinpoint within the sentence what kind of words are important. And you see that it's always mostly the railway. So this neuron kind of seems to represent the concept railway. We have another example of a neuron which represents the concept teacher, but if you look closely at the sentences selected, it's kind of a teacher in a more inappropriate situation. So a teacher having some inappropriate relation with the students, or having an affair with a student. So it seems that this kind of inappropriate teacher is represented by a particular neuron in the network, but maybe the good teacher, which doesn't have this inappropriate, which doesn't show this inappropriate behavior, is represented by another another neuron. So what we also try to do is to get some, to manipulate the model. So we say, okay, the model tells us ice bears. So we wanted the model to complete the sentence. Ice bears live in the output was Arctic, which makes sense. And then we thought, okay, let's identify some neurons. And we identified neurons which are representing the concept coldness, freezing. We identified some neurons which represent the concept dry and the concept candy. And what we did is we deactivated or disabled the neuron for the coldness and activated the neuron for the desert, and then the output changes to desert, right? Because the model then thinks or has more, we've kind of forced the model to answer our question, but to highlight more the warm and dry concept. And and the same goes for candy. The answer is candy store. And it's also very interesting because the completion, the answer is not like candy, but candy store, right? So the concept of location is still kind of present in the model. So the model can answer this question by shifting its focus on sugar and candy. Recently, we also have some work trying to use these explanations to prune our models. So we have a vision transformer, and we know maybe that certain things are important. And so what we tried is to say, okay, if we know that only a part of the model is important, so let's remove the non-important elements. So we have a model trained maybe on 1,000 classes, but maybe we're just interested in the prediction of 10 classes. And what we can do with LRP is to have a very large pruning rate for vision transformers without sacrificing much accuracy. So this is something which we also think about, whether we can, this better understanding of where information is encoded in the model can help us to design more methods for compressing the model for removing information out of the model. And the good thing is that you don't need many samples. So even like if you have 1 or 5 reference samples, you can do it very efficiently. So you just show 5 dogs and 5 cats to the model, and then you can identify the subnetworks which is relevant for encoding dogs and cats, and then you can encode the rest, and the model will still be able to classify dogs and cats very accurately. So I would like to conclude with some remarks. So we have recently like a manifesto written on XAI 2.0. So I think we really need to move explainability to the next level. We need to come up with new types of explanations, which more semantically informative explanations, especially if we interact with large language models. It may be not enough to just apply the methods which we have developed 10 years ago. We need to be creative and also integrate explainability into a bigger pipeline of model debugging or model compression or whatever you want to do with these methods. So explanation is not something which we should do for its own sake, but because we want to reach a bigger goal. And with that, I would like to thank you.